Okay, I want to keep talking about work done on gases and introduce the concept of PV diagrams. So in the last online lecture, I wrote down an expression that the work done by the gas, by the system I'm considering, due to changes in its volume, can be written as the integral from the initial volume to the final volume of P dV. Now, if I assume this is an ideal gas, you could say, well, I know that for an ideal gas, the equation of state tells me that I know the pressure is always related to the density, okay, which I'll write here as the number of particles, N, divided by the volume, times the Boltzmann constant times T. Okay, I could also write it as PV equals nRT. So you could say, well, okay, let me just, if I'm doing an ideal gas, I can just stick it in here. I'll have N times K Boltzmann T over volume dV. Okay, you say, okay, well, can I integrate this? There's the volume right there. I know how to integrate this. The problem is that you don't know what the temperature is doing during the process. Now, it is always true that at any point in time, this relationship holds. Okay, the pressure is equal to NKT, or PV is always equal to nRT at any point in time. But you can't assume that the temperature is held fixed if I change the volume. Okay, so this actually can depend on the volume. As I compress it, certainly I'm putting energy into the gas and I'm going to heat it. Okay, now, so I don't know what the temperature is going to do, so I can't integrate this without knowing more about what's happening. Okay, now what I can do is consider a process. I mean, what matters for the work is the pressure and how it changes with volume. Okay, and so what I can do is introduce a diagram that shows the process in a space that's pressure versus volume. Okay, so if I take a particular, say, take a balloon full of gas, and it has a certain pressure here. Okay, so it's on this point where it has a certain pressure, it has a certain volume. I know what the temperature is from that information. Well, if I know the number of particles too, okay? So I can write down PV equals nRT for this particular location. So we'll call this state 1. What I'm going to do is argue that I'm going to compress this balloon. Okay, I'm going to push on it to compress it. Ultimately, I'm going to go to this state here. So when I'm all done compressing it, the pressure I measure is here and the volume is less. Okay, so I've increased the pressure in the balloon and I have reduced the volume. Okay, now the integral for the work, it matters how I get there. Okay, and how I get there depends on how the pressure changes with volume. Okay, and that is where I need to figure out what else is happening. Okay, so if I'm compressing it in a way that lets heat flow out while I do it, so if I think about this quasi-static compression where I'm putting energy in, and as I do that, compressing it, the temperature is going to want to go up because I'm putting energy into the system. But if it can exchange heat with the outside world, the temperature might go up only so much, or not at all. Okay, if it's very effective at exchanging heat, as we'll talk about, the temperature may not change. If the temperature doesn't change, then I know what's going to happen. I know that P is going to go like 1 over V. So I could draw a line through here that goes like 1 over V. Okay. It could be that the temperature changes in different ways as I go up. So it could be that I heat the gas, and if I do that, then it won't go like 1 over V. Okay. And ultimately I wouldn't necessarily get the same final point in that case, okay, for the same amount of energy that I put in. But let's get back to that later. Let's imagine that this is the path I take. Okay, it may be constant temperature, it may not be. The work that I do in this diagram by pushing it from 1 to 2 is just the integral of P with volume. And so that's really the area here, right? So this area is the work. Okay, now what about the sign? So the area is always going to be positive in this sense. If I just draw this and calculate, I'm not going to find a negative area. Okay, I'm not going to have it go below the axis because I can't have a negative pressure. So the sign is determined by the direction of the process. Okay, so because I go this way, I go from 1 to 2, I go from right to left, I'm going against the volume axis. Okay, the volume axis increases to the right. So I'm turning that around and going backward. And what that means is I have a minus sign for the result here. Okay, so in this case, I would have the work done by the gas to be minus this area. Okay, let me just write it this way. Okay. All right, and so that's consistent because what I'm arguing for here is a compression. I'm compressing the gas. It's going from one volume to a smaller volume. I know that in that scenario, I have to do work to do that. So me as the external agent, I have to do work. So I know the internal energy should be going up of the system, okay, or I should be transferring energy into the system that's net positive. It could leave the system as heat. That's another way for the energy to be converted. But I know that there's energy going into the system in that case. So if I write delta U internal is Q minus the work done by the gas, the work done by the gas here is negative, okay, because I'm going, just as I explained it, I'm going against the direction of increasing volume. That results in a negative integral for the work done by the gas. And so that gives me a positive contribution to the internal energy, which is consistent with what I might expect. Okay. All right. So just to follow up on that, what I'm going to do next, and I'll break out a separate video to do this. I'm going to talk about various types of processes because again, I know that at any point in time during a process where I'm compressing the gas, assuming the key point is that it's quasi-static. And again, what quasi-static means is I can do it very slowly and I allow it to stay in thermodynamic equilibrium the whole time. So as I give it some energy and I allow that energy to equilibrate, okay, within the gas, it may raise its temperature. It may not, but the energy I put in gets converted into thermal energy. And I argue that at every instant in time, I'm in equilibrium. And if that's true, then here I'll write the chemistry version. PV is always equal to nRT. Okay, where this is the number of moles. So that's always true at every point in time. Okay, so if I have one point in time, I can calculate if I have T, I have P, I have V, I have N, they're all consistent with this. But that doesn't mean that they don't change in ways that I don't necessarily know how to predict, okay, as the process happens. So the temperature could go up, it could go down. Now, if I look back at this PV diagram, so one process that I'll talk about first, but I'll leave details to a subsequent video, is if the temperature is constant. So I already mentioned that before. If the temperature is constant, then I know that the relationship between P and V is that they're inversely related. So I can just say alpha, which is some constant over V. So if I want to know a future pressure, I know that because the temperature is going to remain constant as I do this, and I'll explain how that might happen. It has to do with allowing heat to flow out of the system as I compress it, for example. If the temperature is constant, then P and V are just inversely related during a process. Okay, oops. And it turns out, so you get P goes like 1 over V, but this constant alpha changes with temperature. Okay, so whatever temperature I start with. So I can draw these lines of P equal to 1 over V, and they look like this. And this is for different temperatures. So this is T1, this is T2, this is T3. Okay, we call these lines on the figure, we call them isotherms. Okay, for constant temperature. Oops. Okay, so if a process follows a path at constant temperature, so if I start at this point here where I have T1 and I say compress the gas, but I do it so that the temperature remains the same, and that's very specific. I have to make a very special arrangement for that to be true. But if it is true, then I'll just follow this isotherm up, okay, to a point 2 on the curve. Now if I'm not isothermal, and I allow heat to, either not to flow or not enough heat to flow to keep the temperature the same, I can go and cut across isotherm. So I might end up over here, okay, and the pressure might go up more than expected, okay, as I compress it. But isotherms are lines of P equals 1 over V with different coefficients set by the temperature. The coefficient is nRT. Okay. All right. So 2 points that we've made, that PV equals nRT always, but that doesn't mean that you have to keep in mind as I change the volume of a substance, the temperature can change. Okay, and so I need to know more information to figure out how pressure changes with respect to volume. And the other point I made on the previous slide is that when you have these PV diagrams, oops, I went the wrong way. Let's go back. There it is. Okay. All right. The other point is that if I have a PV diagram for a process, I can figure out how much work is done based on the area under the curve that represents the path of the process, and then the sign of the work I get from the direction of the process. Okay. All right. So let me stop with this one, and I'll do another one talking about types of processes.